Okay, here we have a series parallel circuit. Looks complicated, it is not. And you're asked to solve. Now, if you take a moment to really study and analyze the circuit, you will see that it is just a plain series parallel circuit. Let us see if we could go through understanding why it is just a plain series parallel circuit. We will look at this connection, this point. This point, everything along this wire can be considered the same point. They are the same potential. Let's look on the other side. Everything along here can be considered the same connection, the same wire. Let's look at the other side. Everything along here, they're the same. In other words, anything that touching this highlighted section are connected. So we go through the entire circuit doing this. And you will see that the circuit gets reduced. Very simple. Everything along this blue highlighted portion are connected together. And finally, anything along this final highlighted portion, they're all connected together. So this is the first observation you have to make. Sometimes it's not as easy as this, but you have to spend a moment to analyze that part. So let's call this A. Let's call everything along this other highlighted color B. Let's call that C. Let's call that D. Let's call on this side E. So that's E. So now that we've figured out how the current runs, we can see very clearly that this group is in parallel. Now these two are clearly in parallel. But not only are they parallel, notice it is connected, that the 8 ohm resistor is also connected to it. So is the 12 and the 10, but let's concentrate on the 8. Why just limit our concentration to the 8? Because look on the other side, they are also connected. Remember we said when leads are directly connected together, then they are parallel. So we can say that these 3 are in parallel also. Let's look at this 10 and this 12 ohm resistor. Again, the 10 and 12 on the input side are connected together, and the 10 and 12 on the output side are connected together. And so we can say that that's in parallel. What about the 15? Well, we'll talk about the 15 in a second. But here we can see this 20 and this 30, they're connected together on the input side and on the output side. So that's another parallel group. Again, you may ask, what about the 6? Well, we'll discuss that again. And what about this 5? Let's simplify the circuit one stage and see what we get next. So here we go. Okay, so redrawing the circuit and proceeding to calculate these individual group resistances, I get that this bit, this is 2.03 ohms. This bit is 5.45 ohms. This bit is 3.87 ohms. And finally, this last bit is 12 ohms. So what I'm going to do now is I'm going to redraw the circuit, inserting those equivalent resistance that I found in the place. So between A and B, I'm going to put 2.03 ohms. Between C and D, I'm going to put 3.87. Between B and C, I'm going to put the value I got there, 5 point something. And between E and D, I'm going to put 12 ohms. So the circuit now will be vastly simplified and reduced. Now, remember, I use my parallel resistance formula to calculate the resistance of these groups, right? Your calculator has a function called reciprocal, which enables you to go and do that calculation directly. Okay, observe what I've done here. I've removed the parallel branches and replaced them by their equivalents. So what you're seeing here is this group between A and B is being replaced by an equivalent resistor, 3.02. The group between B and C, 5.45, is replaced by a single resistor. Similarly, the 3.87 is replaced by a single resistor. Now, as far as this power supply is concerned, the power supply does not know that I've made these changes, because this 2.03 is identical in electrical behavior to the three resistors R1, R2, and R3 in parallel. Similarly, this 10 and 12, R4, R5 is identical to the 5.45. So electrically speaking, I haven't changed the circuit at all. So we can now proceed to analyze this new equivalent circuit. Again, we study the circuit, analyzing it. We see that A, B, and C remains the same place. But if you look very carefully, you will see that these two are in series. And that combination is in parallel with this 15 ohm resistor. So we have to go reduce the circuit once again. We'll combine 5.45 with 3.87 to make it into a single resistor, reducing that circuit. And we re-examine and see what's in series, what's in parallel. Okay, so you see what we've done? We've combined REQ2, that's the 5.45, and REQ3, which is the 3.87, and I got 9.32. There it is, the new equivalent resistor. Now, you should appreciate now the circuit is getting smaller and smaller and smaller. We want to reduce to a single resistor RL to find out what that single resistor is, to be able to find the total current, the current come out of the battery. Okay, so without hesitation, we proceed, and we notice that these two are in parallel, and I can combine them to form a single resistor. By now I will give you a shortcut to find two resistors in parallel. Two resistors in parallel. So R1 in parallel with R2. The shortcut for them is product over sum. So RT is equals to R1 R2 over R1 plus R2. When you have small nice values, that shortcut is a nice quick tip to remember. We won't use it here now, we're going to use our regular formula because 9.32 is not a nice value. So I'm going to take the circuit out, I'm going to redraw again, replacing this REQ5 9.32 with R6 15 to get a single resistor. And again, the magic continues. So we did some work. We combined the 15 ohm resistor and 9.32 using the parallel rule, or you can use a shortcut, product over sum. That's a useful shortcut. It only works when you have two resistors, bear in mind. And we replace R6 and REQ5 with 5.75. When you do the calculation, that's where you'll get. But notice we still have 2.03 and 12 in the circuit, so we can't trouble them yet. So replacing that parallel combination, we get this. Again, if you look at this circuit, you will see that you have these three resistors in series. How do we know in series? The same current passes through all of them. And you combine these three resistors in series to get 2.03, 5.75, and 12 to get 19.78. So reducing the circuit further, so we remove those three resistors and replace it by the equivalent. And you get this. Notice the three resistors are gone, you replace by just REQ7. Now REQ7 is in parallel with that 6 ohm. Again, you could use your series parallel formula, or you can use the product over sum formula and you'll get that 6 and 19.78 is 4.60. So these two are in parallel. So you replace it by that one. When you combine these two in parallel, you get in 4.60 ohms. That's why that's in that circuit. Finally, 5 and 4.6 are in series, and you get your final circuit to be the total resistance RT is equals to 9.60 ohms. Now, you must go through all these steps and you must redraw because you'll need these intermediate circuits to find branch currents in these things. Okay, so do not shortcut these steps. These steps are most important. So let me go it over again once again. This is our initial circuit. And you can see immediately that there are things you can do immediately. This first group can be combined in parallel to give you 2.03. The second group can be combined to give me 5.45. The third group can be combined to give me 3.87. The fourth group can be combined to give 12. How do I know which to be combined in with which? I follow the connection rule for circuits in series and circuits in parallel. If the ends are directly connected together, as they are here, if you notice, these ends are they're all connected to the green circuit. The ends are directly connected, not just the input, but the output are connected together. That means there's in parallel. Same thing here. It does not appear that way, but the current coming here splits in two, and the two recombine at the junction C. The ends are directly connected together. Again, this does not immediately look like it's in parallel, but look, the ends of the 8, the 12, and the 20, they are directly connected. There's nothing between the connections. Similarly, on the other side, they're directly connected together. The outputs are directly connected together. That makes it in parallel. Well, this one is easy to see. Okay, doing these calculations. Oops, no, do not move that. Doing these calculations, I replace all the resistance with the parallel branches with the corresponding equivalent resistances, and I get this circuit look greatly reduced. But look here in the colored circle, we have two resistors in series, 5 and 3.87, 5.45, so we can go ahead and combine those. Combine them to get 9.32. Now when we redraw the circuit and we look again, we see that 9.32 is in parallel with the 15. And when you combine those, you get 5.75. And that 5.75, when you replace it in the circuit, you notice it's in series with 2.03 and 12 for there. Oops, sorry. Combining that series piece of the circuit into 19.78, I get this. Now you notice that the 19 is in parallel with the 6. Combining it, I get 4.68. Now you notice 4.68 is in series with 5, and I get my final circuit, and this is called the total resistance of the circuit. That is something you've got to be able to do. All problems of this type will require you to do that.